Welcome to Math 201, Lesson 4.6, Part 2, More Unrelated Rates. To summarize our procedures for related rate problems that we first introduced last class, start with drawing a picture, identify which quantities are changing and assign those variable names, list what you know and what you don't know, find a relationship between all of the variables, take DDT of both sides, and then plug in what you know and solve for what you want. Let's do a few more examples together. We're going to begin with an activity, dripping ice cream. Pause the video, try this problem, and when you're ready to go over it, come back and press play. Your friend's little brother likes ice cream, but he eats it really slowly, so the ice cream quickly turns to liquid. Today, he got ice cream in a conical sugar cone, which measures 2 centimeters in radius and 8 centimeters tall. And you glance over and notice that the remaining ice cream fills the cone to a height of 6 centimeters. So draw a figure that illustrates this situation. So let's see, we have a cone, and it has a height of 8 centimeters. And the radius of the cone is 2 centimeters. And then ice cream is in the cone, and it is at a height of 6 centimeters. So liquid ice cream filling this cone. And the height is 6 centimeters. And they did not tell us the radius. So in problem 2, we want to calculate the radius of the ice cream remaining in the cone. It's not 2 centimeters, that's the radius at the top of the cone itself. I want to know this radius. We could maybe label it R. And then I want to use that information to determine how much ice cream is currently in the sugar cone, and they gave us a formula for that. So we can actually use similar triangles to figure out this radius here, because we have this big right triangle here. I could draw it like that, and maybe I'll highlight it. So we've got this big triangle, and then we have a smaller triangle, this one here. So we have similar triangles, and we can use the proportionate relationships in similar triangles to solve for R. So we say by similar triangles, we can say 2 is to 8. So the radius of the big triangle to the height of the big triangle, that ratio should be the same in the similar triangle, radius to height. So this should equal R over 6. And then we can solve for R. So we get 12 equals 8R. So R is 12 over 8, or 1.5 centimeters. And then I want to use that information to find the volume of ice cream in the cone. And volume is 1/3 pi r squared h. And I'm going to put in the r and the h for just the ice cream, right? So the volume of ice cream in the cone, which is a height of 6 centimeters, radius 1.5. So this is going to be 1/3 times pi times 1.5 squared times 6. And that comes out to 4.5 pi cubic centimeters. You also notice that the cone has begun to leak, and it's losing a half a cubic centimeter um, of liquid ice cream every minute. And if your friend's brother stopped eating the ice cream, how long would it take before the cone was empty? Well, we would take the current volume, 4.5 pi, and you need to subtract out what's leaking out, which is a half cubic centimeter every minute. And we want to set that equal to 0. And when you solve this, you get 9 pi minutes. Note that there are three varying quantities here: the volume of ice cream in the cone, the radius, and the height of the remaining ice cream, each of which is dependent on time. I want to write a relationship between the varying quantities, radius, and height of the ice cream in the cone. And I'm going to use similar triangles to do it. So I'm going to redraw my picture, my similar triangles picture. Okay, so the height of the whole cone was 8, and the radius at the top was 2. And then this quantity is changing, so I'm going to call it R. And this quantity is changing, so I'm going to call it H. Radius is changing as the ice cream drips out, and the height of the ice cream is changing as the ice cream drips out. So I can write a proportion to show the relationship here. By similar triangles, we say 2 is to 8 as R is to H, and we get 2H equals 8R, or R is 1/4 H. There's no right way to write this relationship. They just said to write a relationship. You could have circled this one or this one or this one. Okay, for the last question, now we're going to solve a related rates problem. It says use related rates to determine how fast the height of the ice cream in the cone is falling when you first discovered the leak. So you'll need your equation from the previous part to eliminate one of the varying quantities. So let's see, what do I know and what do I want to know? Okay, so they told me the rate at which the ice cream is leaking out, and that is going to be dV dt. It is negative a half. Okay, because the volume is decreasing, so the rate should be negative. And what we want is the rate at which the height of the ice cream is changing. How fast is the height of the ice cream falling? So I want dH dt at the moment we discovered the leak, which is when h equals 6 centimeters. And then my equation that can relate volume and height is going to be the volume of a cone. Volume equals 1/3 pi r squared h. And I'm going to use the previous answer to the previous question where I solved for r. R was 1/4 h in question 4. So I'm going to replace this r with a 1/4 h so that I only have one variable on the right-hand side of this equation. So I have volume is 1/3 pi, and instead of r squared, I'm going to have a quarter h squared times h. And when I simplify this, I'm going to square my quarter and I get a 16th. A 16th times a third is 1/48. Okay, so I'm going to have 1/48 pi h cubed. Okay, so now I have a nice relationship relating what I know something about and what I want to know something about. But the things I know and want to know are actually rates. I need to introduce some rates into this equation by taking d dt of both sides. Okay, so d dt of v is dv dt. And then d dt of 1/48 pi h cubed, I'm going to start with the power rule here, but then I have to remember h is a function of time, so I'm going to have to use the chain rule as well, multiply by dh dt after I do the power rule. So I bring this 3 down, I get 3/48 or 1/16 pi h squared times dh dt. And then I plug in all the stuff I know and solve for what I want. So dv dt is negative 0.5. I'm curious about the moment in time when h is 6, and I want to solve for dh dt. So I get negative, multiply both sides by 16. So I have negative 8 equals 36 pi times dh dt. and then divide both sides by 36 pi. So dH dt is -8 over 36 pi, and I can reduce that to -2 over 9 pi. And my units should be h units over t units. So h was height, that's measured in centimeters. Time was measured in minutes. So this is centimeters per minute. We now have another activity. Try these couple of problems on your own. Pause the video. When you're ready to go over them, come back and press play. The top of a ladder slides down a vertical wall at a rate of 0.15 meters per second. At the moment when the bottom of the ladder is 3 feet from the wall, it's sliding away from the wall at a rate of 0.2 meters per second. How long is the ladder? Okay, so first thing I always want to do is try to translate the words they've given me into a picture. So we have a ladder leaning against a wall. So let's see, we've got a vertical wall, we've got the floor, and a ladder. So we're going to assume that the wall and the floor are perpendicular to each other, and we'll call those distances A and B. I'm labeling them with variables because what's happening is the bottom of the ladder is sliding and the sliding away, and the top of the ladder is sliding down. So these distances are changing. As the bottom of the ladder moves away, B is increasing, the top of the ladder is falling, A is decreasing. The length of the ladder, C, is a constant. Okay, so this is a constant. It's not changing, but we don't know what it is. They're asking how long is the ladder. But we do know that C is a constant. So let's see, what do we know? And what do we want? I know we want C. Okay, they want to know how long is the ladder. What do we know? Okay, we know that the top of the ladder slides down at a rate of 0.15 meters per second. So that means this distance A is changing. So we know the rate. And A is actually a decreasing quantity, so it should be negative 0.15. The rate should be negative because the distance A is decreasing, it's getting smaller. And then they told me that the bottom of the ladder is sliding away from the wall at a rate of 0.2. And it's moving away, which means B is increasing. So it should be dB dt should be positive. And that is when B is 3. Okay, when the moment the bottom of the ladder is 3 meters from the wall. Okay, so I've got some stuff I know. I know some stuff about A and B, and I want to know something about C. So I could use the Pythagorean theorem. So my relationship between all these variables will be a squared plus b squared equals c squared. And I want to introduce some rates because the things I know about are rates. So I'm going to take d dt of both sides, and I get 2a times dA dt plus 2b times dB dt equals. Now, you might be tempted to write 2c times dc dt, but remember, c is a constant. The length of the ladder is not changing. And so c squared is also a constant. It's just a number, and the derivative of a constant is 0. C is not changing, so its derivative is 0. And now I plug in the things I know and solve for the things I want. Okay, I actually don't know A, and I can't figure it out based on the information I have. I only know the value of B. I don't know A, so I'm gonna have to leave that as an A for now. So I have 2A times dA dt, which I do know is negative 0.15, plus 2B I know is 3, and dB dt I know is 0.2, and that equals 0. Okay, so I only have one unknown in this equation, and it's A. It's not the thing I want, but it will give me more information. I can solve this equation for A. So I have negative zero point 0.3a plus 1.2 equals 0, which means that a is 4. Okay, so I know a, it's not what I want, but it is another piece of information. So at the moment of time I'm interested in, I know that b is 3, that was given. I now know a is 4, and I know this is a right triangle, which means I can use the Pythagorean theorem to get c. So this is a 3, 4, 5 right triangle. So I would say 3 squared plus 4 squared equals c squared, and we get c is 5 meters. Question 2. At the moment when the bottom of the ladder is 3 meters from the wall, what is the rate of change of the angle between the ladder and the ground? Okay, so they've given us a little bit of a picture. This 3 is a specific moment in time. That is not a constant. So I'm actually going to cross that out and put a B there. I'm going to put an A here. I know that C is 5. I know the length of the ladder is 5 from the first question. Okay, so now I'm going to write down what do I know and what do I want. So what do I know? I know dA dt was negative 0.15, and I know dB dt is zero point 0.2 when B is 3. I know C is 5. And then what do I want to know? I want to know the rate of change of this angle, theta, between the ground and the ladder. That would be d theta dt. And it's at that same moment in time when B equals 3. All right, so I need an equation that can relate some of the things I know to some of the things I want. Um, okay, so I know a lot of things now. I want to know d theta dt. Um, and the moment in time I'm interested in is when B equals 3. So I think I'm going to use B and the 5 to relate my theta. I'm going to use cosine theta, because it can use the adjacent side over the hypotenuse. I like the 5 because it's not changing. It just makes things less complicated. And I like using the B because I'm interested in the moment in time when B is 3. You could use A, and you'd still get there. You have to use sine theta, but I'm going to use cosine B over 5. Um, and that's gonna help me because I have B, right? I have a B in here, and I'm definitely interested in the moment when B equals 3. So you also could use sine theta. You'll still get there. It just is an extra layer of complication. All right, so now I need to introduce some rates. So I'm going to take d dt of both sides, and the derivative of cosine theta is negative sine theta times d theta dt. And the derivative of b over 5 is 1/5 times dB dt, right? The derivative of 1/5 of b is just 1/5, and then times the derivative of the stuff, dB dt. Now plug in what we know and solve for what we want. Now I have a specific moment in time I'm interested in. That is when b is 3. The ladder's always 5. And when b is 3, the height h, or the height a, will be 4 from the Pythagorean theorem. So there's theta. So sine theta at this moment is 4/5. So I've got negative 4/5 times d theta dt, which is what I'm interested in, equals 1/5 times dB dt, which is given is 0.2. Okay, so I have negative 4/5 times d theta dt equals 1 over 25. Okay, because 0.2 is 1/5. So 1/5 times 1/5 is 1 over 25. And then I just have to solve for d theta dt. I have 1 over 25 times 5 over 4 negative. I can reduce. and I get -1/20. And that, because this is d theta dt, it should be theta units, which is radians, over time units, which is seconds in this question. Okay. And it came out negative, which we should think about whether or not that makes sense. So theta, as we move the ladder away, theta is closing, right? That angle is getting smaller. So it does make sense that the rate of change is negative. There's a sign on the wall that's 10 meters high. At the moment when the bottom of the ladder is 3 meters from the wall, so the same moment that we've been studying for the past two questions, what is the rate of change of the distance from the bottom of the ladder to the top of the sign? Okay, so let's draw a picture of what they're describing. So there's our wall, here's our floor. We've got a ladder that goes partway up the wall, and we call that distance A. And the distance from the wall to the bottom of the ladder was B. The ladder is 5 meters. And then the picture is 10 meters up the wall, so above the top of the ladder. Okay, so if this distance is A and this distance is 10, this distance is the difference, 10 minus A. All right, and then I'm supposed to find out the rate of change between the bottom of the ladder and the picture. So this distance here. All right, we'll call that X. So what do we know? Same stuff as before, all the same stuff. And but this time, what do we want? We want dx dt when b is 3. All right, so I need a relationship between a and or b and x. All right, and I actually do have one. Um, this distance squared plus this distance squared equals x squared, and this is 10. And that doesn't change. So my relationship is going to be 10 squared plus b squared equals x squared. I know some stuff about a, but I don't need, it's information that's not important. Okay. But I also know some stuff about b. So as long as I can relate b, one of my variables with an x, I'm good. So when I take the derivative, when I take d dt of both sides, the 10 squared, the derivative of it is 0. That goes away. And the derivative of b squared is 2b times db dt. And the derivative of x squared is 2x times dx dt. And then we plug in stuff we know and try to solve for stuff we want. So I'm interested at the moment in time when b is 3. db dt I know is 0.2. I don't know the value of x, but I can figure it out from the Pythagorean theorem. So the moment in time I'm interested in is when b is 3, and this distance is always 10. So x would be 100 squared plus 3 squared equals x squared. So x is square root of 109. So 2 square roots of 109 times dx dt, which is what I want to know. So I'll just leave that as dx dt and I'll solve for it. Okay, so 2 times 3 times 0.2 is 1.2 equals 2 times radical 109 times dx dt. And then I'm just going to divide both sides by 2 root 109. So dx dt equals 1.2 over 2 square roots of 109. My units are going to be my x units, which is meters, over my time units, which was seconds in this problem. And you could reduce that fraction, but I'm not going to bother. Just going to leave it.